Okay, while I wait for Miet to come back, did everyone watch the previous recorded lectures from last week? Apologies for that, COVID unfortunately getting in the way. Did anyone have any questions about any of that material before I get started on today's stuff? So it was going through general species interactions models and different types of interactions that we can have. The general setup for a system of two coupled ordinary differential equations. So those represent, say, the population density of one species and population density of another. We're going to be talking about this pretty much always in the context of two different species, but the same tools and techniques will apply to other structured models. So by that I mean, for example, suppose we have you want to model a human population and you want to model juveniles and adults. So children and adults, you would use the same setup, but in terms of there being two ODEs, and we would use the same tools, whether it's looking at finding the equilibria, looking at the Jacobian, analyzing stability, drawing phase planes. All of that is the same stuff, but I'll be framing this in terms of species interactions. Okay, so the Jacobian, had anyone well, maybe I'll phrase it this way. Had everyone met the Jacobian before, or was that something new? Okay, I'm seeing everyone had met it before. Okay, good. And yeah, then we focused on the resource competition model, so Lotka-Volterra competition model, and went through the analysis of that algebraically. And today we're going to be talking about phase planes and how we construct those, and then ideas about competitive exclusion and coexistence when we have two species that are competing for shared resources. What I'll also say about this idea of resource competition, again, I'll frame it in terms of resources because it's easiest to think of that way. So they're competing for the same food source or the same nest sites. It's actually a lot more general. We can have more indirect forms of competition. So for example, two prey species will compete to be if they have a shared predator. So likewise, two COVID variants, topical, I know, they compete each other because they have cross immunity. So they compete for hosts and they compete via the overlap in immunity that they have. So this idea of resource competition is very general. It doesn't just apply to, two birds competing for the same seed. It applies to lots of different scenarios. Okay, I'll make a start. So today we are going to be thinking about these ideas of competitive exclusion, so where one species excludes another, and conversely, what happens and how can they stably coexist with each other. We'll talk a little bit about founder effects, so that's where your initial conditions affect your outcome, and then how we can analyze these systems geometrically using phase planes and direction fields. Okay, so like I just said, we've met the Lotka-Volterra competition model, not to be confused with the Lotka-Volterra predator-prey model, which we are going to be talking about next week. We analyzed the stability of our coexistence equilibrium, and this was using essentially the same process that we did in one dimension. So if you remember, in one dimension, we wanted to look at the stability of an equilibrium by linearizing around that nonlinear system at that equilibrium and seeing if a small perturbation grew in size or whether it decayed. And that was relatively simple in 1D because you can only, in continuous time, that perturbation could either grow or decay. So it was stable or unstable, unstable or stable. And hey, come in. In two dimensions, we've now got more possibilities for how we could move. Okay, so we're not just moving along a line, we're moving in a plane. So that means that we can do things like we can now oscillate, we could spiral in, we can spiral out, we could move around with the same amplitude in a periodic orbit. We can tend towards our equilibrium monotonically, and we can move away from it. So there are a variety of different things that we can do now in two dimensions. Okay, so we're going to be constructing phase planes, which are analogous to our phase line diagrams that we had in one dimension. Just to start with, let's recap what the non-dimensionalized resource competition model was. So before we had this set up with ends, so we had our population size for species 1 and species 2. This is non-dimensionalized now so that our U and our V correspond to species 1 and species 2, but they're normalized according to their carrying capacities. We've managed to simplify down our competition coefficients as well. So we actually just have 3 parameters in this model. We have this S, which tells us about the relative rate of intrinsic growth of species 2 relative to species 1. And then we have these competition coefficients A and B. They give the relative strength of interspecific competition, so interspecific between species, as opposed to intraspecific, which is within a species. Okay, so we can analyze this algebraically, and if we do so, we can draw a table like this, which summarizes the different outcomes that we can have. Okay, so as we vary these A and V parameters, the S parameter, it turns out, doesn't affect our stability at all, which is nice. It only depends on this A and this B. So when let's look at our trivial equilibrium. So this 0, 0. So it's called trivial because both of the species are extinct. Okay, and it turns out that this is always an unstable node. So that means we will always move away from our trivial equilibrium as soon as one of the species at least is present. Okay, so we move away from it in all directions. Okay, what about if we have just species 1 at its carrying capacity? So again, remember this is normalized. When U is equal to 1, that means that N1 is equal to K1. Okay, so that means that species 1 is at its carrying capacity and species 2 is absent. And we refer to this as a semi-trivial equilibrium. Semi-trivial because one of the species is extinct. So we're essentially collapsed back down to a one-dimensional scenario here. Okay. So we can show that if A and B are both less than 1, or if A is greater than 1 and B is less than 1, then we have a saddle. And otherwise, we have a stable node. So there are 2 possible outcomes here. So this was all essentially from the previous lecture. I'm just summarizing what we had before. So with our semi-trivial equilibria, we either have a saddle or a stable node. Let's just write these in for the other semi-trivial equilibrium. So that's when species 2 is at its carrying capacity and species 1 is extinct. Check I'm writing that down right. Yeah. Stable node. And then finally, at the bottom, we have a non-trivial or coexistence equilibrium. And for this one to exist, we need to have A and B less than 1 or A and B greater than 1. This means that both of our numerators and denominators here are either positive or negative. Okay. And in this case, in these middle 2 columns, it's not realistic. So those conditions at the bottom are not satisfied. If they're both less than 1, we have a stable node. And if they're greater than 1, then we have a saddle. So stable node means you're being pulled in, whereas an unstable node means you're being pushed out. A saddle is kind of strange, but it looks like a saddle. If you imagine like a saddle on a horse or a Pringle, you're being pulled in one direction and pushed away in the other. Okay, so sort of a biological interpretation of, say, one of these semi-trivial equilibria being a saddle. When you've just got one of the species present, you're pulled towards the carrying capacity for that species. But in this example here, when A and B are less than 1, as soon as the other species is present, you move away from that point. Okay, so you only get pulled towards it when there's one of those species there. As soon as the other one is there as well, then you get pulled away from that. So that means that there's only sort of one path that will bring you right into that semi-trivial equilibrium. So it's stable in that sense, but it's unstable in all other directions. So you get pulled away from it. Okay. As always, just stop me if you want me to explain everything. Okay, so a bit more interpretation about what do all of these things actually mean. We've got, A's and B's greater than or less than 1. Well, if we look at these two scenarios here, if A is less than 1 and B is greater than 1, or vice versa, in other words, if we're in this middle column here, then there are no conditions where both species coexist. It's because this bottom shaded thing here is not realistic. So there's no coexistence equilibrium here. So that means they can't coexist. And we either have a saddle or we either have a saddle at or a stable node at each of our semi-trivial equilibria. Okay, so one's a saddle, one's a stable node. And then if we change the order of A and B here, sort of, for example, if A is greater than 1 and B is less than 1, then there is a stable node down here and a saddle for the other values of A and B and vice versa. Okay. So what this is telling us then, because we can't have both species competing, if A is less than 1 and B is greater than 1 or vice versa, then we have competitive exclusion. So in other words, one species is out-competing the other and driving the other one extinct. Okay. If we now think about this non-trivial equilibrium, so when can we possibly have stable coexistence? We'll only see stable coexistence when A and B are both less than 1. That's the only time when that is a stable node. We'll talk about what that means in a moment. When A and B are both greater than 1, we have a saddle. So we do get pulled towards that coexistence equilibrium in one direction, but we get pushed away from it in another. So stable coexistence occurs if both of our interspecific competition coefficients, A and B, if they're less than 1. But we get competitive exclusion again if A and B are greater than 1, but this time it occurs because of something called a founder effect. And a founder effect is basically your initial conditions determine your outcome. So a founder effect tells us essentially that the species that by and large has more individuals to start with ends up winning. So there's a dividing line where if you're on one side of that line, again, think of it like a ridge line across between two valleys, there are two attracting states. And depending on which side of that ridge you start on, it will tell you which valley that you end up in. Okay, so this is like our bistability that we had before with our spruce budworm model, that where you start off affects where you end up. Okay. So let's do a little bit more interpretation, thinking about what these competition coefficients mean then. So we defined the parameter A to be alpha 1, 2 over alpha 1, 1. And remember, alpha ij is just essentially the strength of competition from species J to species I. Okay, so alpha 1, 1 is the strength of competition between individuals of species 1. Alpha 1, 2 is saying what is the relative impact of species 2 on species 1. So how much individuals from species 2 are harming the growth rate of species 1. Okay, so just going all the way back up to these equations up here. This A here, A is equal to alpha 1, 2 over alpha 1, 1. And this B is equal to alpha 2, 1 over alpha 2, 2. It's telling us something about the relative strength of interspecific competition relative to intraspecific competition. Okay, so what happens if we go back up to our non-trivial equilibrium here? We note that in the reason that we need to have this condition AB less than 1 or AB greater than 1 for our non-trivial equilibrium to exist is because of this AB term in the bottom, as well as the 1 minus A and the 1 minus B on the top. So what does that AB actually represent? Well, AB is just going to be alpha 1, 2 times by alpha 2, 1 over alpha 2, 2 times by alpha 1, 1. So to have AB less than 1, for that to be true, to have stable coexistence, we need alpha 1, 2 times by alpha 2, 1 to be less than alpha 1, 1 times by alpha 2, 2. So all I've done here is I've set this to be less than 1 and then rearranged it. Okay. All these alphas are positive, so it doesn't change the sign of that inequality. So this is actually something quite profound, because this is saying that the product of our interspecific competition, so competition between species, has to be less than the product of competition within those species. If this is true, then we get stable coexistence of those species. So the effects of competition for resources within your species have to be stronger than those with another species in order for those species to coexist. That's something that's quite a profound statement to be able to make from a relatively simple model that tells us, okay, if we see, say, two squirrels coexisting, then it's like telling me that, say, the gray squirrels and the gray squirrels coexist with the red squirrels, perhaps because they maybe eat some slightly different food. Or a classic example of this is Darwin's finches, which I don't think I have in here. Maybe I had them in the previous lecture. Darwin's finches, where Darwin observed on the Galapagos Islands that different finches had evolved different beaks, and those beaks allowed them to specialize on different seeds. And so this idea of coexistence ties in with ideas about species evolving to occupy distinct niches, and those occupying distinct niches means that they have weaker competition between those species as opposed to within the species. And so that by itself enables or facilitates coexistence. So this tells us something about ecology, but it also tells us something about evolution. Okay, we're now going to think about some graphical interpretations of this, and hopefully that'll help illustrate what's going on. So we're going to draw some phase planes, and I've actually changed Wednesday's lecture. I was going to talk about evolution a bit in the context of this model. I'm going to focus tomorrow on a bit more on phase planes. This will be in the midterm, so there is a practice midterm. We'll practice this now. We'll practice this as well tomorrow as well. So it's a good time to ask any questions if you're not sure about how we construct these. Okay. Okay. So to construct a phase plane, this is analogous to a phase line diagram in 1D, but we're now in 2 dimensions. So we have to draw a plane rather than a line. And we still want to think about, okay, we're going to be sketching some arrows on here, and those arrows are going to tell us where we're going to tend towards in the long term, okay? So we'll be able to work out where our equilibria are, and those arrows will tell us, are we tending towards those equilibria? Are we moving away from them? And how are we doing so? Are we spiraling, or are we going there monotonically, okay? So in order to sketch these phase planes, we need to work out our Nullclines and then our direction field. So I'm going to go through today how we construct this, and then tomorrow I'll talk a little bit more about interpretation, about what we mean exactly by, say, our Nullclines. So let's focus today on how we actually construct it. So question here. So we usually find the direction field. So our direction field is essentially telling us if you're stood at one particular point in our phase plane, and that particular point represents, say, the density of species 1 and species 2. We could have any combination of those densities. At that point, our direction field is a vector telling us which direction we're moving in. So it's telling us our instantaneous rate of change, okay? And that can point in any direction. We usually don't care about the magnitude of it when we're sketching these things. We care about the direction of it. Is it going up, down, left, right, or some combination of those? Okay. We usually try and then sketch our phase planes by finding our direction field on our Nullclines. So you imagine you're stood on one of our Nullclines, and our Nullcline is representing, in this case, du dt is equal to 0, or dv dt is equal to 0, right? So you imagine that you're stood on one of these Nullclines, and by definition of being on a Nullcline, either u must not be changing or v must not be changing. So the reason we look to calculate our direction field on these Nullclines is if du dt is equal to 0, the only 2 directions we could possibly have are straight up or straight down. Okay, if we've got our axes orientated like this, if this is my u and this is my v, if I'm on a Nullcline where du dt is equal to 0, there's no movement going left or right by definition, right? Du dt is equal to 0. So I can only be moving up or down. So I don't know what that nullcline might look like. Maybe it looks like this. This curve could be a straight line. But I know that whatever point I am along that nullcline, no matter where I am, I can only be moving up or down. So say I move up like this. That's a lot simpler than, say, picking a random point in this space here and having to work out, okay, well, what is my du dt? Maybe it's going up, and what's my dv dt? Sorry, yeah, my du dt is going right, say, and my dv dt is going up. And then I have some diagonal line like this, diagonal vector, okay? It's much easier to just work out one of these rather than both of them. Likewise, if we're on dv dt equals 0, I'll sketch this in purple, say, suppose we've got a line like this. In this case, we can only go left or right. If dv dt is equal to 0, by definition, there's no change in my v. I can only change in my u. So for example, I might have arrows that look like this. In fact, I'll change these arrows here on this right-hand side to make it more correct. Can anyone tell me what this purple dot is that I'm sketching on here?
Both of them are 0?
Both of them are 0, exactly. So what does that mean I have?
No.
What do we call it if both of our equations will be equal to 0? You look like you were about to raise your hand, or you're stroking your hair. I'm not sure. If du dt is equal to 0 and dv dt is equal to 0, what do we have? An equilibrium. Yeah. So when we have our nullclines intersecting, we have an equilibrium. Suppose this is du dt is equal to 0. I'll draw this. dv dt is equal to 0. Okay, and so here both of them are equal to 0, so we have an equilibrium. Can anyone tell me, suppose we also have a nullcline that looks like this. Is this an equilibrium here? This brown dot? No? Why not?
Because both of them du dt is 0.
So yeah, so du dt is equal to 0, but dv dt isn't equal to 0. So just make sure, just because you have an intersection between nullclines doesn't mean you have an equilibrium. It has to be nullclines for the different equations, okay? So that's one of the reasons why I usually sketch them with different colors, because then I know here, okay, when there's a red and a purple line intersecting, then I have an equilibrium. Please let me know if the colors are an issue if you are colorblind, and I will try to adapt them, okay? Okay, so that's the general idea of a phase plane. We're drawing our nullclines, we're working out what the directions are on those nullclines, and then, for example, in this case, I could imagine, okay, what happens if I was starting off with this particular value of u and v, and this gray dot here? Well, I know in this region of the space, I must be moving up and to the left. So I know that any trajectory here is going off somewhere like that. Likewise, if I was, say, starting off over here, I must be moving to the left and down, because that's where the arrows are pointing. So I must be moving left and down, left and down, left and down. Eventually, I cross this red nullcline here. I know that when I cross that nullcline, I have to be moving down, because that's where my arrows are pointing. So now I'm moving down. What about in this region here? I must be going down and to the right. So I'll go like this, okay? So by working out what our direction field is on our nullclines, we can work out what our trajectories look like, and hence what is the stability of our equilibrium. Turns out this case happens to be saddle by the looks of it. Okay. So let's actually analyze this model and work out what our nullclines and our direction field are. So for species 1, we're going to set du dt equal to 0. So if we go all the way back up to here, where the equations are, setting this equation here equal to 0. So that means that either u must equal 0, or the bit in the brackets must equal 0. So that means u is equal to 0 is one of my nullclines. My other nullcline, we had so we had 1 minus u minus av must equal 0. So that implies that u must equal 1 minus av. Or I could write this as v is equal to 1 over a times by 1 minus u. And generally, I will tend to write nullclines in the form of whatever is on my vertical axis as the thing on the left-hand side. That's completely arbitrary. It's just that, typically we write straight lines in the form y is equal to mx plus c, as opposed to x is equal to 1 over m plus c over m. Okay, they're the same equations. I hope I've not made any mistakes. Sorry, there should be a y. They're the same equations. Should be a minus c. But typically we write a straight line as y is equal to mx plus c. We often write y is equal to some function of x rather than x as a function of y when we're sketching them. Okay. Either way, these things are the same. Okay, so we've got two nullclines for species 1. So now we can think about, okay, suppose we're stood on this first nullcline, u is equal to 0. And we want to know what is our direction field. So because u is not changing, we know that we have to be going up or down. And so we want to know what is the sign of dv dt. So we don't care about the magnitude of dv dt, we just care about the sign. So let's think about what dv dt is when we're stood on this nullcline u is equal to 0. Well, my equation for dv dt is sv times by 1 minus bu minus v. But we're told that u is equal to 0 because we're stood on the nullcline where u is equal to 0. So that means this term here is going to equal 0. So on the nullcline, sorry, for some reason my pencil is not working. Good. On the nullcline, we're going to have sv times by 1 minus v. Is that clear what I've done there? Okay, so I know that I'm stood on this nullcline. Imagine, for example, you're on this nullcline here, this red one, this red curve. Any point along that curve corresponds to where du dt is equal to 0. Okay, in this case, my nullcline is u is equal to 0. We substitute that into my equation for v, so dv dt. And then we want to know the sign of this. Well, we're restricting ourselves to non-negative values because we're talking about population sizes. So this is going to be positive if v is between 0 and 1. And it's going to be negative if v is greater than 1. I don't care about the magnitude, I just care about the sign. So in other words, when v is between 0 and 1, on this nullcline, my arrows are going to point up. And if v is greater than 1, on this nullcline, my arrows are going to point down. Okay, and we just go through this process for all our other nullclines. It's a little bit more complicated in this case here when v is equal to 1 over a times by 1 minus u. So that's my second nullcline here. But it's the same process. We look at dv dt is equal to sv by 1 minus bu. Let's see, which way should we write this out? We'll write it in terms of v's. So again, we have bu minus v. We're going to substitute in this value of v. We're going to have s over a times by 1 minus u times by 1 minus bu minus v, which is 1 over a times by 1 minus u. Okay. That's a little bit trickier. I'll leave that as an exercise, but we can show this. This is quadratic in U. So we can find out what the values are. In this case, it turns out that dv dt is negative if u is less than 1 minus a over 1 minus ab. And it's positive if u is greater than 1 minus a over 1 minus ab. And that should look somewhat familiar. These inequalities down here. This 1 minus a over 1 minus ab was my value for u at the coexistence equilibrium. So this is telling me that the sign of dv dt is changing as I move through that coexistence equilibrium. Okay. And that should kind of make sense, right? Our coexistence equilibrium occurs when we have the intersection of these nullclines. And on one side of the nullcline, dv dt is going to be positive. On the nullcline, dv dt is going to equal 0. And then on the other side of that nullcline, dv dt is going to be negative. Okay, so the fact that we pass through an equilibrium, we're passing through a nullcline, and therefore we must be changing the sign of our derivative here. Okay, maybe spend a couple of minutes here, see if you can do the same for species 2. In fact, just do the first one. Just do the one where v is equal to 0, because again, we'll end up with a quadratic at the bottom, which is a little bit messier. Okay. So du dt is equal to u times by 1 minus u minus ab. Because we're on a nullcline for species 2, dv dt is equal to 0. So we want to know, we're not moving up or down at all. We want to know whether we're moving left or right. So we need to look at the sign of du dt on this nullcline. So on the nullcline, v is equal to 0. We substitute v is equal to 0 here. So we have 1 minus u times by u. And just like we had above, this is going to be positive if u is between 0 and 1. And it's going to be negative if u is greater than 1. Who managed to get that? Yeah, okay, good. Sometimes it takes a few goes if you're not confident at doing these to figure out how to work out the signs. Okay, on the other nullcline, v is equal to 1 minus bu. Sorry, my computer decided to restart mid-lecture, which is always great. This one, again, is a little bit more complicated. We're going to end up with du dt is equal to u times by 1 minus u minus a times by 1 minus bu. So again, this is going to be quadratic in u. It's a little bit tricky to work out what this is. But again, like before, we can show that du dt is going to be positive. So we move to the right. If u is less than 1 minus a over 1 minus ab, and it's going to be negative if u is greater than 1 minus a over 1 minus ab. Again, we see that this is the u coordinate at the coexistence equilibrium. It changes sign there. Okay, so we now have all the ingredients we need to have a go at sketching the phase plane. So let's have a go at doing that. And we're going to do this for the case when a and b are both less than 1 to start with. So first thing, set up your axes. You have u on the horizontal axis, b on the vertical axis. This is arbitrary. It doesn't matter which way around you do this. You get the same qualitative result. And let's see. I'm going to sketch my du dt nullclines in green. I'll be consistent. So we had a nullcline for du dt when u is equal to 0. So that's this vertical line here on this axis. And we also had one, let's just go back up here to our nullclines. We had a nullcline here, v is equal to 1 over a times by 1 minus u. So this is a straight line. It's got a negative slope because there's a minus sign in front of the u. And the slope, the intercept occurs when u is equal to 0, v is going to be 1 over a. And we're told here that a is less than 1. So I know that my 1 over a is going to be some value here greater than 1. Can add some more labels here. So this is 1 over a here. When v is equal to 0, u is equal to 1 along that line. So it intersects the horizontal axis when u is equal to 1. Okay, so that's nullclines for du dt. And don't forget your labels. So du dt is equal to 0, these green ones. Now let's do our nullclines for dv dt. So for dv dt is equal to 0, we had a nullcline when v is equal to 0, so along the horizontal axis. And our other nullcline was v is equal to 1 minus bu. So here, again, this is a negative, a straight line with a negative slope because of the minus sign in front of the u. B is going to be less than 1. When u is equal to 0, v is going to equal 1. So we're going to intersect the vertical axis at 1. And because b is less than 1, when v is equal to 0, u is going to equal 1 over b. Okay, so what does that look like? We're going to intersect the vertical axis at 1 and the horizontal axis somewhere down there. Okay. So the fact that a is less than 1 and b is less than 1 tells me where these intersections are relative to values of 1 on the axes, okay? So because a is less than 1, 1 over a is going to be greater than 1. And because b is less than 1, 1 over b is going to be greater than 1. Okay, I can now sketch on where my equilibria are. So the intersections of these green and red nullclines. And I have 4 equilibria. So those are my nullclines, those are my equilibria. The last thing to do now is to think about my direction field. So let's go back up to here for nullclines for du dt. So du dt are equal to 0, which means there's no change in b, and I'm just moving up or down. So I've got these arrows here. Let's do the first nullcline when u is equal to 0. So when v is between 0 and 1, it's over here, v is between 0 and 1, dv dt is positive, so we're going to move up. And when b is greater than 1, I do not know how to get rid of that. There we go. When v is greater than 1, we're going to be moving down. So on my phase plane, I can draw in some arrows. When v is between 0 and 1, on this nullcline, u is equal to 0, I move up. And when we're greater than 1, we move down. I can repeat that process. Let's do it now for just this red nullcline, dv dt is equal to 0 along the bottom. It was a similar case when u is between 0 and 1, when u is between 0 and 1, du dt was positive. So we move to the right. And when it was greater than 1, du dt was negative, so we move to the left. Okay. At this stage, I usually like to sketch on just some lines onto my nullclines just to make sure that I'm putting the arrowheads in the right direction. So on my red nullclines, I can only be moving left or right because dv dt is 0, okay? So I know that I have to be crossing this nullcline horizontally. And then conversely on my green nullcline, du dt is equal to 0, so I have to be moving up or down. Okay, so let's pick one of our nullclines. Let's go with, we'll keep the order here. Let's go with du dt first. So on our diagonal nullcline when du dt is equal to 0, so the diagonal green line, we found that we were moving up when u was greater than 1 minus a over 1 minus ab, and moving down when it was less than that value. And that value corresponds to my coexistence equilibrium. Okay, so when I'm to the right of my coexistence equilibrium and on that green diagonal line, I must be moving up. So these arrows down here have to be moving up. So I'm to the right of this coexistence equilibrium in the middle. U is greater than that value, so I'm moving up. And conversely, when I was to the left of that value, so when u is less than 1 minus a over 1 minus ab, on this side, my coexistence equilibrium, you have to be moving down. Because if you move along this nullcline, this green nullcline, and I pass through the equilibrium, note that the direction of my arrows change. So if you know what the direction that they are on one side, you automatically know what they are on the other side. So there's a lot of deduction that we can do. We don't necessarily have to do all the algebra to find out what goes on all the nullclines, and we'll talk about this more tomorrow. In fact, we only need to find out the directions on 2 nullclines. We can deduce the rest from there, okay? For dv dt on this diagonal nullcline, what did we have? We had du dt was positive if u is less than 1 over a minus 1 over 1 minus ab. So that means that we're going to be moving to the right when we're to the left of the coexistence equilibrium, and we'll be moving left when we're to the right of the coexistence equilibrium. So arrows here on the left, we move right, and then on the right-hand side, once we pass through that coexistence equilibrium, we move in the other direction. We can also think about what happens if we're in each of these regions. Suppose we're in this region down here, bounded by these nullclines. Because of the continuity of these functions, we know that we can't be changing our sign of du dt or dv dt unless we pass through a nullcline. And in this region here, we don't pass through any nullclines, right? So that means that we have to be moving up and we have to be moving to the right everywhere in that region. Some places we'll be moving more up than we are to the right, and some places more to the right than we are up. That depends on the relative rates of these things, but we know that we're not moving down or left, okay? If we now think about, say, this region here, I'll just zoom in a little bit. If we think about this region here, we've crossed a nullcline, and that nullcline was a red one, so dv dt was equal to 0. So in this region here, we have to be moving down and to the right. Okay. So in the region at the bottom, we were moving up and to the right. We've crossed through this nullcline here where dv dt was equal to 0. We're now moving down to the right. And you can just keep repeating this process. So that's why we don't necessarily need to work out all of our nullclines. We now think about this region up here. If I'm moving clockwise, if I go through this green diagonal nullcline, I now must be moving down and to the left, sorry, down and to the left. And then this bottom region, the last one, I must be moving up and to the left. So I've managed to deduce all of the points in this plane. I know exactly where I'll be moving. I'm going to be moving some combination of up or down and left or right. Okay. The very final thing we can do is then think about some possible starting points. So suppose my initial conditions are over here. I'm in this region in the top right where I'm moving down and to the left. So, for example, I'm moving down to the left. Maybe I move like this. Suppose I start over here. I'm moving up and to the right. Well, up and to the right, maybe it takes me in like this. And we could do this for all of these regions. We can cross these nullclines. So for example, suppose I start over here in the top left. I'm going to be moving down and to the left initially. So I know that my trajectory is going to start like this, but I must cross this green nullcline vertically, going down, and now I'm moving down and to the right. And so perhaps I move in like this. So all of these trajectories, no matter where I start off, if I have positive u and v values, I have a stable node. I always move in towards this coexistence equilibrium. I don't oscillate on the way in here. I move in gradually. It might be possible that you cross one or two of these nullclines, but you're not spiraling in. Okay. Okay, there is one other version to look at, which is a phase plane when A is greater than 1 and B is greater than 1. I'm going to leave that as an exercise. And in fact, the self-study problem is looking at the other combinations as well. We've actually already found our direction field. Okay, so you don't need to find the direction field again. All that's changing is the orientation of our nullclines. So note that when my red, if I just think about the diagonal nullclines, when my red diagonal nullcline is below my green diagonal nullcline, these directions will still be the same. Likewise, when my red nullcline is above my green nullcline, I'll still be moving left on that red nullcline. I'll still be moving up on that red nullcline. The difference is when I vary my values of A and B is the intercepts of the axes are going to change. So that means where the green line is above the red line is going to change. But the arrows only change. The arrows will still have the same orientation. So it matters when the green line is above the red line in this case, but where the green line is above the red line will change. So bear that in mind when you have a go at sketching the other phase planes. Okay, that's it for today. Let me know if you have any questions. If not, I will see you tomorrow.